So here's our general second order transfer function. We could find where the poles are by solving the denominator equal to 0, solving the characteristic equation. And you'd find that the poles are at negative zeta omega n plus or minus j omega n times the square root of 1 minus zeta squared. And we often replace that part here by omega d. So zeta is damping ratio, omega n is natural frequency, but omega d, we'll find, is the damped natural frequency. So if you give the second order system a step input, it'll look like this if it's underdamped. Right? If it's an underdamped system, so zeta is between 0 and 1, then you get a response like this. The period of oscillation of this underdamped response is given by 2 pi over the frequency of oscillation, which, because there's damping present, is the damped natural frequency, omega d. So that value there is the same as the frequency of oscillation of the damped response. So 2 pi over omega d. Compared to what the undamped response is. So if there's no damping, and zeta goes to 0, right, because there's no damping, then the response has a frequency of omega n, the natural frequency. There's one other type of frequency, which is usually the forced frequency. If you had an input that was a sinusoid of a certain frequency, then you would see that frequency in the response as well. But we're looking at step responses. All right, so that's the period of undamped oscillation, and then we're at the period of damped oscillation. Now, that basically gives us some information about the frequency of response given, or when compared to the transfer function, because we can tell there's certain pole locations that give rise to these particular characteristics, omega d and omega n. Next thing is to have a look at how the poles change as you change omega n and zeta. And this is a really good diagram to remember, right, to memorize. So for example, if we keep omega n constant and only change zeta in the system, and we've seen this because I looked at each of the cases in the last lecture. If you keep omega n a constant and just change zeta, the amount of damping, you go from an undamped system where the poles are sitting on the j omega axis or imaginary axis. I often call that j omega axis because of the imaginary part over here. But on the imaginary axis, poles go from here, and there's only 2 poles, right? And as you change zeta, the poles move along this locus, it's called. So the locus is the path traced out by poles as you change some parameter. So the root locus, path of the roots of the denominator, trace this path. So they go along here, and they go in a semicircular arc. You go travel around in an arc where the radius of that arc is omega n. Right there. We start out here at imaginary parts omega n, and then the radius continues to be omega n, and zeta goes from 0, and if you increase zeta, it goes to 1 when they meet together as repeated roots, and then it's critically damped. Alright, so it's undamped here, and then when it's in this section, it's underdamped. When it goes here, it's critically damped. If you keep increasing zeta, these 2 poles break apart along the real axis. One goes towards the imaginary axis, but never quite reaches it, and the other one goes towards negative infinity. And there you have the family of pole locations as zeta changes, all in one diagram. So it's really nice to remember this. Now you can calculate what the value of zeta is at any point, say in this configuration where it's underdamped. You can calculate zeta by the angle that the line between the origin and the pole makes to the real axis. That angle theta, you can calculate zeta as cosine that angle. Because if the angle is 0, cosine 0 is 1, right? Zeta is 1 when that angle is 0, and those poles are now both touching the real axis, and cosine of 90 degrees is 0. When that angle is opened up completely, and the poles are purely imaginary. Right, so that's a really good diagram to memorize. Sketch it out in your own time, try to remember that. Now we're going to use that information as we look at how we move poles and see how the movement of the poles affects certain transient response. So let's take a look. If we have an underdamped system and then we move the poles just vertically, they have to be in complex conjugate pairs, right? So it's the real axis is a mirror, is a line of reflection. Then you move the poles, you should stretch them out, you're just changing the imaginary part. Remember that the imaginary part is given by, well, let's actually go back and make sure that's okay. The imaginary part is given by omega d, right? The damped natural frequency. So what we're doing is we're going to be increasing omega d while keeping the real part the same. The real part, let me just write it out here, S, the roots of the characteristic equation are given by negative zeta omega n plus or minus j omega d. Okay, so those two poles right there. So negative zeta omega n is the real part of the pole, and I'm going to keep that constant and only change omega d. So what you can do is you can look at all the different performance specifications, which I have in a previous page, settling time, etc., and you'll notice that the settling time is a function of the product zeta omega n only. Which means that if I'm keeping zeta omega n constant and I move the poles, I'm keeping the settling time constant. Which means the family of responses that you get when you've moved the poles just vertically looks like this, where in each case the settling time, the 2% settling time, stays exactly the same. And what's really changing is the amount of overshoot that we have and the rise time. There's a slow one that reaches at the same settling time as this fast one that has oscillations. Because what we're actually preserving is this envelope of decay. So if you draw a curve between the peaks that you see in the response, you find it's actually an exponential function. That one there, or you could look at the one that goes from 0 in the lower peaks, the undershoots. That's an exponential function whose shape is determined by the real part of the poles. And you can see that if you look at the general solution for the response of a second order system. Let me pull that up here. This is an Alyssa formula. Here's the general response for a second order system to a step. What I've called sigma d is zeta omega n. So that decay envelope, which is a factor in the equation, is a function of zeta omega n. So that determines the amount, how quickly it decays, how quickly that sinusoid decays to 0. And that's what determines the settling time. Okay, so you've seen that case. Next case is if we hold the imaginary part constant and just move the poles further to the left along a horizontal plane. So if you move it horizontally, you are keeping omega d constant and varying the real part. And if you keep omega d constant, you could look in the equations, you'll find that it's the peak time that's a function of omega d alone. That's the time that you hit the first peak in your response. So the family of curves you get as you move the poles are these ones, shown in different colors, where you have the same peak time but different peak value. Peak time is pi over omega d. The peak time is actually half the period of oscillation. Because it starts from a dip, a trough, I suppose, in the sinusoid, goes to a peak, that's half a period. It goes down here, that's a full period. That guy there is t, I think I've called it, I have called it t in my notes. Capital T, the period of damped response. That's one full period, and that's half a period, and that's why they're related. Like that. You can go peak to peak or trough to trough to calculate the period. Okay, and the next case is if you keep the angle constants. So if you draw a line between 0, the origin of the complex plane, and the pole, or one of the poles there, if you keep that angle of that line constant, then you're keeping constant damping ratio because of the formula theta equals inverse cosine of zeta. If you keep a constant damping ratio and you look in your equations, you'll find that both the percentage overshoot and the peak response are a function of zeta only. So the family of curves look like this. They have the same peak, but different speed of response. So they're interesting trends that you need to understand, observe, remember, in order to quickly analyze the system. That's second order.